Hi, this is Team 22. In our final lab project, we focused on recreating the deep-sea anglerfish in our Lego Spike robot. Deep-sea anglerfish are fascinating creatures, thriving in the harshest environments on Earth where sunlight doesn't reach. Their most striking feature is the bioluminescent lure, powered by bacteria, that dangles above their mouth to draw prey closer until it's devoured. With a mouth that can stretch to swallow prey larger than itself, the anglerfish has perfectly adapted to its extreme environment. Experience the anglerfish beyond the ocean's depth through our Lego Spike Prime robot. Designed with a rounded body, bioluminescent bulb near its mouth, and the ability to swim slowly and stop near its target, this neurorobot recreates the anglerfish. We replicated the glowing bulb using the color sensor and crafted an arm extension for its mouth, powered by a motor that moves up and down to mimic the anglerfish's bite. These predators conserve energy by remaining stationary, using their bioluminescent lure to catch unsuspecting prey. Inspired by their efficiency, we designed a neurorobot to replicate this behavior. Our experiment focuses on mimicking anglerfish behaviors through neurorobotic design principles: sensory motor integration, exploration versus exploitation, and invigorated versus withdrawn. The robot explores with random velocities and turn durations, ensuring effective prey detection. Our learning rate experiment reflects how young anglerfish learn to eat and expand their diets. Using the Rescola-Wagner function with a learning rate of 0.10, we conducted 6 trials with shrimp, reward value 5, and 6 trials with both shrimp and fish with a reward level of 10. Our graph shows that fish weight exceeded shrimp weight, demonstrated diet expansion. The action selection loop guides our robot's behavior based on color detection: red for shrimp, yellow for fish, and green for plants. The robot's stomach variable stops food seeking at 98% fullness, matching real anglerfish behavior. We ran 6 trials, 3 with our plants, 3 with, lasting 12 to 30 minutes each. Our neurorobot demonstrates slow swimming, energy conservation, and precise prey capture behavior. Despite challenges with color sensor calibration and movement control, our robots successfully emulate anglerfish behavior through sheep designed through sensors mimicking the anglerfish's ESCA and sensory intake for prey detection. Embodiment was achieved via eating stimulation, slow movement, and the color sensor acting as adaptive lighting like the ESCA lure. Value systems and reward mechanics were integrated by assigning values to fish and shrimp, updating stomach levels during trials, and implementing basic avoidance behavior for plants. Exploitation occurred when sensing food below 98% stomach fullness, while exploration manifested during general movement or post-satiation. The Rescola-Wagner experiment demonstrated learning and memory through progressive rule assessment of prey. Sensory motor integration was shown through color detection: red, yellow, fish, green, plants, triggering specific motor responses for eating or avoidance. The robot displayed invigoration during food search and withdrawal during reaching fullness. This retains all key 8 principles such as cheap design, embodiment, value systems, reward punishment, exploitation exploration, learning memory, sensory motor integration, and invigoration versus withdrawal, while being more concise.